you to understand about mass defect and binding energy, nuclear physics. You need to know what the atomic mass unit is, Einstein mass energy equivalence, mass defect, binding energy per nucleon, graphs, problems. Okay, here we go. Let's start off right now with the atomic mass unit. We've talked about this briefly before, but I'm gonna talk about it again so that you get it hammered in. What have we traditionally measured mass in this class? No, not really. Kilograms. Thank you very much. Kilograms, because that's kind of a more kind of I said mass, I thought. Yeah. But Newton is a measurement of weight. On an atomic scale, the kilogram is way too large, and it does us no good. So we're going to create a whole new unit. We're going to call it the Unified Atomic Mass Unit. And we're going to give it that little letter U. And we're going to define the atomic mass unit as 1/12 the mass of a carbon-12 atom. Why did they choose that? I don't know. Maybe because we're a carbon-based life form. But that's just it. This is a classic IB question. Define the atomic mass unit. Oh, it's 1/12 the mass of a carbon-12 atom. Boom, there's your point. Give me a 7. All right? Okay. Remember that. Easy points. Okay? If we were to do this and figure it out, we would see that one atomic mass unit is equal to 1.6605,402 times 10 to the negative 27 kilograms. You don't need to memorize that because it is in your data booklet. I'm pretty sure the conversion factor is in there. I would not expect you to memorize that. But I do just want you to know that an atomic mass unit is very small. It's very useful when we're dealing with atomic and nuclear physics because it's about the size of the things that we are dealing with, such as protons, electrons, and neutrons. So in atomic mass units, here are some numbers. This will be extremely helpful in your homework. If you don't have these numbers written down, they are in your textbook. I think on maybe the second page of the chapter. But you will use these numbers a lot. Notice that a proton and a neutron have an atomic mass unit of about 1, but it's not exactly 1. It's a little bit more than 1. Not for some of this nuclear homework. You're going to need to be more specific than just using 1. You'll need to go out to this much detail. And it might also be in your data booklets. Is it? Okay. Notice that the electron has very, very little mass, but we've already talked about that before. So let's talk about this idea of mass defect. Mass defect, which is sometimes represented by the Greek letter delta. I believe that's a lowercase delta, I think. Or is it a sigma? Oh, man. Okay, let's see. Okay, here's where things get weird. You ready? And this is what Vince was just kind of talking about, even though he didn't know that's what he was talking about. If I look at a nucleus, the nucleus will tend to have less mass than if I was to add up the mass of all the protons and neutrons individually. Okay? So if I take, say, carbon-12, 6 protons, 6 neutrons, and I find the total mass of 6 protons and 6 neutrons, that'll be greater than the mass of a carbon-12 nucleus. There's mass missing. That's called the mass defect. The amount of mass that's missing is known as the mass defect. So you look at that. Missing mass. Mass defect. Okay? So I can calculate the mass defect, and this is why you needed to know those numbers, 1.00554, whatever, out to that decimal point. Because if I look at the total mass of the nucleons that make up a nucleus, and I subtract the mass of that nucleus, then I've gotten the mass defect. And that's going to be really helpful for a lot of things. Recognize that when you look at a periodic table of the elements and you look at the mass, it's usually the mass of the atom, which is the nucleus plus that many electrons. So you got to take that into account sometimes when you're doing problems. You might have to subtract out the electrons from a mass on the periodic table if it's not the nuclear mass, but it's the atomic mass that they're giving you. So if the mass is different, the question then comes, where did it go? What happened to that mass? It turns into energy. And what's that energy doing? Holding the nucleus together. Okay? The missing mass is the energy needed to hold that nucleus together. And what Einstein told us is that mass and energy are interchangeable. E equals mc squared. It's a famous equation. People can cite it all they want. What that equation says is that energy equals mass. Mass and energy are interchangeable. We've talked about the law of conservation of energy. No. Energy is not conserved. We've talked about the law of conservation of mass. No. Mass is not conserved. But energy and mass are conserved together. Mass can be converted to energy. Energy can be converted to mass. And the equation that allows us to do that is E equals mc squared. Okay, so binding energy is the energy that's holding the nucleus together according to the equation E equals mc squared. If you can figure out how much mass is missing, then you can calculate how much energy is holding that nucleus together, or how much energy it would take to rip that nucleus into its constituent parts. Okay? That's called the binding energy. If I use Einstein's equation, E equals mc squared, and I use my mass in kilograms and speed of light in meters per second, then it'll tell me how much energy I get in joules. And we could actually do this conversion if we wanted to, and we would find that one atomic mass unit of energy, or one atomic mass unit of mass, is the equivalent of 931.5 million electron volts of energy. That's a conversion that you will use a lot in these problems with nuclear physics. I think it's a conversion that's also in your data booklet. Okay. So binding energy is the amount of energy holding a nucleus together, or it can also be thought of as the amount of work needed to separate the nucleons of a nucleus. That's called the binding energy. All of them? All of them. The total binding energy would be the total energy. If I looked at the total mass defect, figured out how much energy that was equivalent to, that would be how much energy it would take to completely separate out all those nucleons. Okay. The more, can't do that yet. The more binding energy a nucleus has, the more stable it is. The more binding energy, the more stable it is. The more energy holding that nucleus together, we say that that's a more stable nucleus, okay? So what we can look at then is, rather than looking at because generally a bigger nucleus is going to have more binding energy, just because it's got more nucleons. So what's more important to us is the binding energy per nucleon. How much energy per proton or neutron is actually holding that nucleus together? That will give us a really good indication of the stability of the nucleus. Brian. So let's look at this. This is a graph you will see lots of. It's muy importante. You should think about it, learn about it. Okay. This is a graph of the average binding energy per nucleon of certain nuclei. Okay. Notice that we start down here with hydrogen. It's got a binding energy of a little over 1. And then we go with deuterium, which is hydrogen with a neutron. And it's a little bit more. And then there's helium. This is kind of interesting right in here. You can't see it real well on this graph, but notice that helium is more than lithium. I think is lithium next after helium? Yes. Notice that helium has a higher binding energy per nucleon than lithium does. Quite a bit, actually. It drops back down here. This is, well, it's a noble gas, but it's also, this is why we have alpha particles. This is why when things decay, they give off an alpha particle instead of a lithium particle, because it's a more stable nucleus. It's a much more stable than anything around it, really. But the other thing you should notice is that this all increases. Most nuclei have a binding energy per nucleon of about 8 mega electron volts per nucleon. And here is our friend iron, which is right at the top of the curve. Okay? In order to get more stable, you need to go to iron. So this stuff down here, like uranium-238, it becomes more stable by falling apart into smaller pieces. That's called fission. Small stuff becomes more stable by globbing together. That's called fusion. Okay? But ultimately, the most stable place is way up here. That's where everything wants to be. Okay? I think that might be why we have an iron core. That's a reasonably good proposition.
But then why don't all planets have an iron core?
I think it depends on what they started with, I guess. Okay? So most nuclei are about 8 mega electron volts per nucleon of binding energy. The helium one is pretty large. I talked about that. That's why we have alpha particles. That's why an alpha particle is a helium nucleus, because it has it's relatively stable.
Wait, is that 8 megavolts per
nucleon. And iron's at the max. Energy will be released when going either way. So if I have big nuclei that break down, they will release energy. If I have small nuclei that are globbing together, that will release energy. And that's the process of nuclear fission and nuclear fusion that we'll talk more about. What else can we talk about here? Radioactive decay. So we talked about the types of radioactive decay, you guys. And basically the mass of the parent nucleus is greater than the mass of the daughter products. There's missing mass. There's a mass defect when something decays radioactively. And that mass is converted to energy, according to equals mc squared. And that energy gets presented as kinetic energy. The daughter products have kinetic energy. That kinetic energy came directly from the mass that was lost. And that's why the alpha particles and the beta particles and the gamma rays are moving at such high speeds, because of the mass defect. Okay? Kinetic energy tends to be how it presents itself, yeah. All right, let's try it out, you guys. Let's try it out. Here you go. Practice problem. Well, come on, Vince. So remember to take into account that oftentimes when you're given the mass of an atom, that includes the electrons. So that's something to consider, unless it specifies that it's the mass of the nucleus, okay? If this is the mass difference, could we calculate the binding energy in that nucleus? What would you do? Multiply it by, there's an easier way to do it. 931.5, and what will that tell you? No, because this is an atomic mass unit. This is what? Megavolts. Mega electron volts. This will give you your answer in the mega electron volts of energy holding that nucleus together. You get it in joules. Right. So what did you get? 28.296345. How about 28? Okay. Now, 28.3, this is the binding energy of the entire nucleus. That's how much energy is holding that nucleus together. What if I wanted to know the binding energy per nucleon? What would you do? Just divide by 4. Righto, you guys are brilliant. It's awesome. What do you get? 7.0 something?
7.08. No, it's a 4.
That's all right. Whatever. That is, on average, how much energy per nucleon is holding it together. Okay? Or how much, this 28.3 is how much energy it would take to break apart the whole helium nucleus.
But would it take 7.08 to break one?
It's a good question, and I honestly... All right. There you go. There it is. Try it at home. Try it at work. Try it with your friends. Try it with your family.